And so you look up, let's say the first one here, look it up and go, son of a gun. Even though I have no education in physics and my grade 9 science teacher thought I was an idiot, my equation is identical to this one called the Lorentz-Fitzgerald contraction equation, an actual equation used to calculate how much an object will contract in length based upon velocity and c. And so you go, wow, that's amazing. So then you look up the next one and go, wow, my equation is identical to this one called the time dilation equation. They call it dilation as if time is kind of stretched out and dilated, right? In other words, time slows down, they call it dilation. But the equation's the same. Wow. And I have no education in physics whatsoever. I just used what I thought was common sense. What's interesting is, though, the letter C in the world of physics does not represent constant motion. It represents the speed of light. But they do say that the speed of light is the fastest speed at which it can move across space. Well, constant motion determines the maximum speed at which it can move across time, any other direction, including the maximum speed at which it can move across space. So they seem to be one and the same, except for light is across space. In this case, you can change, it cannot be just spatial, you can also move across time. But the magnitude of motion appears to be the same. In other words, it's the same as the speed of light, which is approximately 300,000 kilometers per second. Therefore, to represent this constant motion, we can say that this much space will represent 300,000 kilometers, and therefore this much depth across time represents 1 second. In other words, let's say we have two people. One decides to take his constant motion and go this direction across space, and the other guy decides to take his constant motion and go in this direction. And they both leave this point at the same time. One eventually covers a distance of 300,000 kilometers, and since the speed, this constant motion here, is equivalent to 300,000 kilometers per second, the other guy will therefore travel across 1 second. One covers a spatial distance of 300,000 kilometers, the other covers a distance across time of 1 second. So in other words, as well, 300,000 kilometer depth across space is equivalent to the depth of 1 second across time. So now we've related everything here as far as measurements go to this constant motion. And if you recall, I've made the length of my spaceship the same length as this. Therefore, my spaceship is a very long spaceship. It's 300,000 kilometers long. Okay. Now, taking all that into account, the next thing we'd like to do is to calculate how much the object is extending across the dimension of time. Well, you notice that C is going in this direction, the direction of our traveling here, right? And that extends across this much space. So we have a VC ratio. But we're interested in extension across time, which is at a 90-degree angle. Well, what a coincidence. Relative to C, this is at a 90-degree angle, and I've made it the exact same length as C. Therefore, the ratio between B and T is the same as the ratio between V and C. And so the equation required to calculate how much is extending across time would be V over C. Now, just to speed things up, the magic number, the magic speed you would have to travel to make time tick at half speed like this here is 260,000 kilometers per second. This is approximate. So again, this one is your speed of light. This one here is your velocity. So those are that's the magic number. If you put these numbers into this equation, you'll find that time is ticking at half speed. So delta t prime, that time period, would be half of delta t. And if you put those numbers into the first equation, you find that it actually does contract to half length. Because when you do this equation here, you find it turns out to be 0.5. So L times 0.5, or delta t times 0.5. So Therefore, V over C would be 260 over 300, which turns out to be 0.866. So of that 1 second, a convenient single unit of time, time period, 1 second, this spaceship is extending across 0.866. In other words, a significant portion of the 1 second. Now, not every object is going to be 300,000 kilometers long, so we have to add to that equation times L over C. So if this was, let's say, 300,000, which is what we started with, you'd have 300,000 over 300,000, which equals 1, so you'd still have the same result. However, if I reduce this down to, let's say, 150,000 kilometers, this would be 150,000 divided by 300,000, which gives you 0.5, so it would be 0.5 times 0.866, which would give you 0.433, so it would be extending across half as much as this one does, half as much across time. Now, since C is repeating twice here, we can change this to C squared and just reduce this to L. So there's the final equation, V over C squared times L. I'd like to clean that up a bit. So we have V over C squared. Trying to clean one up and the other one's worse. V over C squared times L. Okay, so now we have that equation. We can calculate, no matter what the length is compared to this one, we can calculate exactly how much it extends across time. If it's even longer than this, it could be extending across more than a second. It's a very long object. Okay, so the next step now is to wonder how light and constant motion work together, because they both appear to be the same magnitude of motion, but one's fixed across space, the other one is not. So to do that, we put experiments right on top of the geometry. So we'll start by putting a clock right at the very end here, and it's monitored by Mr. A. Then we put a clock right at the other end, which is monitored by Mr. B. Now let's say these are atomic clocks, so they're super accurate. They were constructed in the middle, synchronized, and moved off to the ends. And now they're going to check to make sure the clocks are still synchronized. And to do that, Mr. A at 12 o'clock noon is going to send a burst of light across to Mr. B. Now this is 300,000 kilometers long, and the speed of light is 300,000 kilometers per second. So Mr. B should receive the light 1 second after Mr. A had released the light, the burst of light. And sure enough, he does. When the light reaches him, his clock says 12 o'clock noon plus 1 second. Then at 12 o'clock midnight, he sends a burst of light over to Mr. A, and sure enough, the light reaches Mr. A when Mr. A's clock says 12 o'clock midnight plus 1 second. And so they shake hands saying, yes, our clocks are synchronized and our spaceship is definitely 300,000 kilometers long because it takes 1 second for light to go from one end to the other. Then they fire the spaceship rocket engines and get the spaceship going in this direction. Thus the velocity becomes 260,000 kilometers per second. Therefore, what they want to do now is to repeat the experiment. Now, first of all, we're going in this direction across space, so therefore this is the front, and this is the rear. And then we have the clocks, clock A, clock B. And the first thing you notice is the clocks aren't synchronized anymore. Clock A is lined up with this point in time. Clock B is lagging behind in time all the way down here. And so that means that clock A is ahead of clock B by this much time, because I've placed the clocks right at the ends. So they're not synchronized. Now, to an external observer, when clock A, the guy at clock A is going to release a burst of light again at 12 o'clock noon, to an external observer who's at rest in space, he sees a spaceship coming along, which is 150,000 kilometers in length because it shrunk to half length. Then he sees a burst of light released, which is traveling across at 300,000 kilometers per second, the speed of light. And therefore he notices that it takes approximately 3.73 seconds for the light to go from one end to the other, because the light is only moving 40,000 kilometers per second faster than the speed of the spaceship. So 150,000 kilometers divided by 40,000 kilometers per second equals 3.73 seconds. So it takes longer than a second from his point of view. On board the spaceship, clocks are ticking at half speed, so you'd think they'd measure half of that. So that's that divided by 2, which equals 1.866. But that's not entirely true because the clocks are not synchronized. Mr. B is lagging behind Mr. A by 0.866. Therefore, he will be missing this much from the actual measurement. So to see what his clock says when the light reaches him, you have to subtract the offset, minus 0.866, which equals 1.000 seconds. So from his point of view, Mr. B, everything seems to be completely normal because the light reached him supposedly 1 second after the time it was released by Mr. A. So this seems strange. Let's verify it. So Mr. B sends a burst of light back to Mr. A at 12 o'clock midnight. Now to an external observer, it was at rest in space. He sees the spaceship going this way and the light is going this way. Right? So the total velocity of the light relative to the spaceship is the two combined. In other words, 560,000 kilometers per second. So 150,000 kilometer length divided by 560,000 kilometers per second equals 0.268 of a second, 0.268. So to an external observer, he sees going from the front to the rear in a very short time period, not like the other way around. But on board, of course, they would only measure half of that, so you divide that by 2, which equals 0.134. But not to forget, the clocks are not synchronized. When Mr. B releases it at 12 o'clock midnight, Mr. A's clock already says 0.866 after midnight. So to see what his clock says when the light reaches him, you have to add the offset. So that's plus 0.866, which gives the result of 1.000 seconds. 1 second. So from their point of view, everything seems to be the same.